Okay, good morning. We'll go with the problem related to stiffness method, a beam problem, wherein settlement of the supports have been given to us. Okay. So that's the beam what we have. So here this is 40 kilonewton and 30 kilonewton. And this is 12 kilonewton per meter. And we have this as 3I, 4I for this span, and 2I over here. This is 4 meters and 2 meters. So in this case, C so what we have is the downward settlement of support C is 30 mm. Okay, so we need to analyze this by stiffness method and find out the bending moment and draw the bending moment diagram for the beam. Okay, so the degree of kinematic indeterminacy dk comes out to be 3 in this case. Okay, that will be theta b, theta c, and theta d. Okay, so if you identify those independent displacements, these are the independent displacements. Rotations at B, C, and D, 3 joints. Okay, now with that, we need to take the coordinates for this beam. So we'll assign the coordinates over here wherever the independent displacements have been identified at those points. Okay, so here are our coordinates. So the first coordinate will come at B. Okay, so that will be the coordinate number 1, and the second coordinate is corresponding to rotation at C, coordinate 2, and we have the third coordinate at D. Okay, So these are the coordinates in case of a beam. So now we'll be writing the matrices over here. So what matrices we come across is the force matrix and the displacement matrices. Okay, so this is our A. Okay, right. So first is displacement matrix. So what we have is here. So this is delta. Okay, so this delta will be having these independent displacements, that is theta b, theta c, and theta t over here. So this will be our displacement matrix. Okay, next is the force matrix, what we have to come across, or we have to get these elements of the force matrix. Okay, so the first force matrix what we'll find out is this p dash matrix. Okay, that is the forces in our coordinate due to the loads applied on the member. Okay, so we have this concentrated load and the UDL which has been applied on the member, and along with that there is a displacement or the settlement of the support C what is given to us. Okay, so considering all these loads and the applied displacements, we'll find out what are the forces which are coming in the coordinates. Okay, so for this first is we'll consider the ends to be fixed and we'll find out the fixed end moments. So we have to find out MFAB, okay, which is minus WL by 8 over here. So that will be minus 40 into 6 divided by 8. Okay, so how much this will be equal to, and MFBA will be simply WL by 8 plus WL by 8 minus 30. This one, is it minus 30 kilonewton
Yes,
meter?
sir.
Okay, and this will come out to be, if you substitute the values, so this will be coming out as plus 30 kilonewton meter. Okay, and in member BC we have MFBC. Okay, so what will be MFBC in this case? So first is due to this UDL minus WL square by 12. Okay, and since C is settling down, there is a settlement of this support C by 30 mm. Okay, so this is the settlement over here. So what will be the moment that will be developed in the coordinate due to settlement? So this settlement is going to affect span BC and CD. Okay, so if you look at this settlement, okay, so the rotation about B will be clockwise. Rotation of the member about B is clockwise. So whatever the settlement value is given to us, we'll take it to be positive. Okay, and the moment developed due to the settlement is given by minus 6 EI into delta by L square. Okay, minus 6 EI delta by L square. That is the value of settlement what we have. Delta is the value of settlement here. Okay, so what will be this equal to MFBC? This part what we have here minus WL square by 12, it is due to the UDL which is being applied on the member BC. Okay, and this minus 6 CI delta by L square, okay, So that is because of the settlement which is taking place at joint C, right? So for this it is UDL intensities minus this is 12. So 12 into span is 8 meters, WL square by 12. 12 is the intensity into 8 is the span minus WL square by 12 minus 6E. Okay, what is the I value for this span BC? 4I. 6E into 4I, okay, divided by 8 square into 30 mm. I want it in terms of meters because span are considered in meters here. Okay, so what will be that? 0.003 meters. Okay, 3 by 1000. Okay, so this is how much? This is 64. What about this value? Minus 6ai delta by L square. The member is being rotated in clockwise direction here. Okay, about this joint B. For that purpose, the delta is taken to be positive. Okay,
Sir, delta value is 0.03.
0.03 comes out as 0.03. 0.03. Check it. 0.3, 0.03, or 0.003. I want it in mm. Okay, 30 mm, 0.03. Right. So how much it comes out? MFPC keep yourself muted. Just tell me the answer. Once you have calculated, tell me the answer.
Nice. Mary. Oreo. Minus 64 minus 0.011 EI.
Okay. EI value has to be taken here. So I'll give you the EI over here. So EI, okay, you take it as just a minute. I'll give you a value of EI.
तुमचे नंबर
Okay, you take this to be 2.2 into 10 raised to 16 Newton mm square. If you take this EI as 2 into 10 raised to 16 Newton mm square. Okay, so if you take it in kilonewton meter square, what it comes out? So I think this will be 10 raised to minus 6 raised to minus 9. Okay, you substitute this one and check what will be the value of our moment. The moment we'll get if our EI is 2 into 10 raised to 7 kilonewton meter square. I think that is coming very high. Let me take a suitable EI value. I'll tell you it. Okay, you take this to be 1 into 10 raised to 3 kilonewton meter square. In this case, what it will be? The moment EI value 1 into 10 raised to 3 kilonewton meter square. How much that will be total moment?
minus 75.25.
Okay, minus 75.25 kilonewton meter. Okay, and for this it will be 12 into 8 square divided by 12, W square by 12 plus W square by 12. And here also about C, what is the direction of rotation due to settlement? It is clockwise only. So delta will be still positive here. So 6 EI, that is 6E into 4I into delta by L square. Okay, so that is 0.03. So what will be our MFCB?
52.75.
Plus 52.75 kilo Newton meter. Okay, so this is a fixed end moment for span BC. For span CD, MFCD, how much it will be? So MFCD, due to the concentrated load of 30 kiloton minus WAB square by L square, okay, minus 6 EI by L square into delta. Okay, so this will be minus 30 into 4 into 2 square divided by 6 square minus 6E into 2I. For span CD, it is 2I divided by 6 square into delta. So what we have here, the rotation, okay, it is anti-clockwise. So for this, it will be minus 0.03 delta. Okay, for span CD, about joint C, the rotation of the member due to settlement is coming out to be anti-clockwise. So delta will be taken negative, minus. So because of that, what will be our moment?
Minus 3.33.
Minus 3.33 kilo Newton meter. Okay, and MF DC. Okay, so it will be plus W A square B by L square minus 6 E I by L square into delta. Okay, so this will be 30 into 4 square into 2 divided by 6 square minus 6E into 2I divided by 6 square into minus 0.03. So this is our MFDC,
36.67.
36.67 kilo Newton meter. Okay, so that is the fixed end moments now, what we have. Okay, so once we have got the fixed end moment for all our spans, now I can go for finding what is my P1 dash. Okay, that is force in the first coordinate. Okay, so what I have for P1 dash is I have to take MFBA and MFBC. Okay, so MFBA 30 here and MFBC minus 75.25. So plus 30 minus 75.25. So that will be minus 45.25 kilonewton meter. This is the force in the first coordinate because of the loads which are applied on the member. Okay, MFBA plus MFBC and P2 dash. What we come across this P2 dash, what we have. So second coordinate is here. I'll be adding MFCB and MFCD. Okay, so MFCB plus 52.75 and MFCD minus 3.33. These two will come in the P2 dash plus 52.75 minus 3.33. 52.75 minus 3.33. So this will be equal to
49.42.
49.44 kilonewton meter. Okay, and third coordinate we have P3 dash here, which is nothing but MF DC only. We have only one member connected in the third coordinate. It is DC. So MFDC is 36.67. So that is our value of P3 dash, 36.67 kilonewton meter here. Okay, so from this I can now write what is the P dash matrix here. This is the first force matrix what we have developed. So P dash matrix what we come across is this is minus 45.25 and 49.44. This is 36.67 P1 dash, P2 dash, and P3 dash. This is the P dash matrix. Okay. So after this, what we have next is to go ahead with the stiffness matrix. Okay. So we need to find the stiffness matrix in this case now. So what we have to do is we need to start giving unit rotation. All our coordinates are corresponding to rotation here. So we'll take each coordinate at a time, one by one, give unit rotation in that coordinate, and find what are the forces in rest of the coordinate. Okay. So here in this case, the first coordinate. Okay. I'll be taking the first coordinate. So what I have in first coordinate is two members which are coming over there. That is member BA and member BC. So for that, what I'll do, I'll have to rotate BA and BC by 1 unit rotation. Okay. So this is our first coordinate at joint B. Okay. And while you are doing this, you should not allow any rotation in the other coordinates. Okay. In second and third coordinate, we are not going to allow any rotation. Okay. So here is the first coordinate and the members which are connected at the first coordinate. And this is the A, B, and C. At C, our second coordinate is there. So we'll lock the rotation at joint C because I don't want any rotation to take place in second or third coordinate. Only in the first coordinate, there will be 1 unit rotation given here. And that too in the direction of the coordinate. It should be in the direction of the coordinate. So this is the coordinate direction clockwise. So what I'll do is I'll rotate this member in the clockwise direction about joint B. Okay, so now I have given the rotation, 1 unit rotation in the first coordinate here. Okay, so after doing this, what you have to find out is what are the forces which are developed in first, second, and third coordinate. Okay, so if I determine the force in the first coordinate because of unit rotation in first coordinate, it will be giving me the K11. Okay, the first element of the stiffness matrix K11. So this is given by 4 EI by L. Okay, so we have all come across this term 4 EI by L. So substitute the respective I values. It is 3I and 4I. Remember AB, this is 3I, and for this it is 4I here. Okay, so what I am doing is I am rotating both members by 1 unit rotation. Okay, so what is the force required here? It is 4E into 3I divided by 6 for member BA. Okay, I have to rotate this member by 1 unit. So for that, the force required is 4 EI by L. So I substituted the I and L value for member AB here first. 4E into 3I by 6 plus what for this member? What is the force required? 4E into 4I. This is for BC divided by 8. So this is what K11 will be. So this will be 3 EI. Is it 3 EI? Confirm this one. I'll not substitute the value of EI at this point. So if you find the force in the second coordinate, if it is 3I, 4EI.
4EI is K11.
Okay, so this is 4EI. Okay, and now we'll go with the finding what is the force in this second coordinate because of unit rotation given in the first coordinate. So this is given by 2EI by L. Okay, so that will be 2E. Okay, where is my second coordinate? At this joint C here. Okay, so I'll be taking the properties of member BC. Okay, I am not having any properties related to member AB because there is no coordinate at A. We are not concerned with A. We are only concerned with finding force in the second coordinate, which is at this point C. Okay, so what is the properties you have to consider is for the member BC, the member which is connected first to the first and second coordinate. So you have to take the properties of that member. So 2EI by L or 2E into 4I divided by 8. So what is this K12? So this will be 4 to 8. EI just EI.
Yes, sir.
Okay. So this is one more stiffness element. Okay. Along with this, what we have to find is what is K13 here. Okay. What should be the value of K13? K13. I have not drawn the next member here because it was not required. Even if you look at this beam, okay, if I have given a unit rotation at B in the joint B, what is the force developed here when C is locked? Any answers for that? This will continue. It is the next member is here. Only thing is I have not shown that. Okay, just think of this member is there, CD is there. What should be the force at joint D where the third coordinate is there? What may be the expression? Yes. What may be the formula expression for finding that force? Even that coordinate, you should not allow any rotation over there. That is also law. Okay. Can you have any guess for that? Force in the third coordinate when unit rotation is given in first coordinate here. Yes. Yes, you can tell. What is the answer? 2EI. Someone was telling that.
minus 6 EI by L square.
Minus 6EI by L square. This is actually what is happening over there. Yes, any other answers for that? Third coordinate. Yes, it is 0, 0. Because beyond this support, you are not allowing any force to transfer. This itself is a fixed support here. Okay, so everything is taken up by this support only. Okay, after this, there is nothing which is no force has been transferred here. See, in this span CD, we are not coming across any displacements. No rotation is taking place in this span CD. So no displacements means there are no forces only here. Okay, so K13 will be 0 here. force in the third coordinate will be 0 because it will be stopped over here. You are not allowing any forces to further transfer up to point D or up to the third coordinate. You have fixed the second coordinate. Here at C, a fixed support has been provided here. Okay, so beyond this, there will not be any displacement taking place. Okay, so no force will be transferred up to D here. Okay, so K13 will be 0. Is that okay? So after you are given unit rotation in the first coordinate, now we'll take up the second coordinate here. What you have to do in the second coordinate is again apply unit rotation over there and find forces in the first and third coordinate. Okay, so second coordinate is at C. Okay, we'll go for giving unit rotation at C and determine what are the forces in first and third coordinate. Right, so A is already fixed. Okay, and since there is no coordinate coming over there, I don't have to worry about that. Only thing is I have to give unit rotation in the second coordinate and no displacements or rotations are allowed in first and third coordinate. So here is my second coordinate. Okay, now I'll apply unit rotation in the second coordinate and in the direction of the coordinate. All our coordinates are in clockwise direction, so we are going to give the unit rotations in the clockwise direction only. So this is the unit rotation in second coordinate. Okay, so here we are given 1 unit rotation at C. Okay, this is C, this is A, B, C, and this is D. So our second coordinate was at C. At that point we are given the unit rotation and no rotation in first and third coordinate. Okay, so now what is our K22? Directly we can go for finding K22. K21, 1, 2, we have already determined that. K22, so what you have 4 EI by L here for this. So here it was, I think, 4I. For this it is 4I. And for this I think 2I. So as 2I. So it will be 4E into 4I divided by 8 for member CB. Okay, plus 4E into 2I divided by 6 span of 6 meter for CD. Okay, so I'm rotating 2 members about a joint, so I'll have to apply a force of 4 EI by L for each of the member. Okay, so I and L for the respective members CB and CD has been substituted here. So how much this will be?
3.33 EI.
3.33 EI. 3.33 EI. Okay. When you are working with this stiffness matrix, it is better you don't substitute this EI value here. Okay. Next is what we require is what is K23. K21 is already there with us. K12 and K21 are same. Okay. So that is due to the symmetric property of the stiffness matrix. So I don't have to find K21 in this case. What is K23? It is 2 EI by L. Okay. Third coordinate is here. Okay, at D. Okay, so what is the force in the third coordinate? When unit rotation is given in first coordinate, it is given by 2 EI by L. So what is the member which is connected between second and the third coordinate? It is CD, this member. So I'll substitute the properties of that member CD. 2E into 2I divided by 6. Okay, so this is our K K23.
0.67 EI.
Okay, 0.67 EI, right? So that is it. Now what we have is, when unit rotation is given in second coordinate, we are determined forces in second and third coordinate, which is giving us another two elements of our stiffness matrix, K22 and K23. Next, what we have to do, we need to take up the third coordinate here now. So here what we have is the third coordinate. So I'll lock the first and second coordinate. I'll not allow any displacements in the first and second coordinate. Okay, and I'll give unit rotation in the third coordinate and in the direction of third coordinate. That is what I'm going to do now. So this is our end A with the fixed support. Okay, so B, where my first coordinate is there, I have restrained all the displacement at B. I have made this as fixed support over here. And C, we have the second coordinate. So at C also, we'll provide a fixed support so that no displacement will take place in the second coordinate. And at D, we have the third coordinate here. Okay, so here what we require is, I want to rotate this by 1 unit. Okay, so in the clockwise direction, because coordinate 3 is also in clockwise direction. So now I given that unit rotation in third coordinate. You have this third coordinate, second coordinate, and the first coordinate. So unit rotation is given in third coordinate. Here is the property 2i for this member. This is D. Okay, so I require what is K33. If I just find K33, that is enough for me. After I get this K33 value, I can write what is my stiffness matrix. Okay, so here 4 EI by L. That is how you find the K33 value by this expression. So in this case, 4E into 2I divided by 6. Okay, so what this comes out as?
1.33 EI.
Okay, 1.33 EI, right? So I have K112, K33, and rest other elements with me. Okay, so all the 9 elements are there with us. So now we'll go for writing that matrix. Okay, so the stiffness matrix. So we can arrange them in this order. Okay, can you give me what was K11? It was 4 EI. I'll keep this EI outside here. So here it was 4. Okay, K12 and K21, it was just simply EI. So it will be 1. And K13 and K31, 0. Okay, and I think K22 was also 4. What we had K22, it is 3.33. Okay, 3.3. Is that correct? K22. So this is 3.33. And what about K23 and 32? It is 0.67 EI. So 0.67 and 0.67. K33 I have here 1.33. Okay, so this is what, this is your entire stiffness matrix. Okay, what is the order of this stiffness matrix here? It is of the order 3 by 3. We had 3 independent displacements, theta B, theta C, and theta D. Corresponding to that, we have the stiffness matrix of order 3 by 3. Okay, that is how the order of stiffness matrix is governed. Okay, so you don't have to write this, just for the information you should be knowing that. So this is the stiffness matrix. Now, what we require is the condition of equilibrium will be considered. Is that okay? Any problem with the stiffness matrix? These values, what we have written here? So you take the condition of equilibrium in the matrix form. So net force in any coordinate will be equal to P delta forces due to the displacements plus due to the loads which are applied on the member. Okay, so this further can be written as this is stiffness multiplied by the displacements will be P delta plus the P dash matrix. Okay, so we can take this. What we actually want is what is our delta. So I can express it as K inverse. Okay, so that into P minus P dash. P minus P dash. Okay, so what we require is this P matrix. So what is P matrix now? For that we'll have to look into this P, okay, which was there here. So if I take this beam, right? So here what you have, first, second and third coordinate are there. Okay, are there any forces which are applied directly in the coordinate? Okay, so those forces will come in P matrix. Okay, P1, when I want to find out P1, I look into the first coordinate. This is my first coordinate at B. So this is a rotation here. Coordinate is representing a rotation. So is there any couple at B applied in this beam? No. So P1 is 0. Similarly, second coordinate is at C, which is a rotational coordinate. Is there any couple applied at C in this beam? No. So P2 is also 0. Third coordinate is here, okay, at D, which is also representing a rotation of a member. So is there any couple at D in this beam? So there's no couple which is applied at D in this beam. So P3 is also 0. Okay. So like that, we'll be considering these elements of the P matrix. Okay. So what I'm getting here is for my problem, in this case, what you have, this P matrix is a null matrix. 0, 0, 0. All the elements of P matrix are 0. Okay. So now what you have to do is substitute these matrices. Okay. And then uh, solve them. Okay. And find what is theta B, theta C, and theta D. Okay. So that solution of the matrix, I'll leave it to you. But if you have any doubt in this developing the matrices, force matrix or either the stiffness matrix, you can clear those doubts. Okay, we can solve this matrix. This is not a big issue. This can be solved. Inverse and matrix multiplication can be done. Okay, so if you have anything other than that, please unmute and ask me. You can also put your attendance, those who are there in the chat. So this is when you have settlement. Settlement will come in your P dash, this matrix, P dash matrix. Okay, they are the forces which are developed due to the displacements applied in the member. Okay, what it comes out if you do the inversion and solve it. This is inverse of this. Okay, P minus P dash, what it comes. So just the signs of this P dash matrix will change, that's all, because P is 0. So it will be 0 minus 45.25, which is plus 45.25, 0 minus 49.44, minus 49.44, 0 minus 36.67, minus 36.67. Okay, 45.25 minus 49.44 minus 36.67. So if you solve this, you'll get to know what is theta B, theta C, and theta D. 49.44, 36.67. Okay. So P minus P dash. I've taken P minus P dash. This is P minus P dash. Okay, P is 0. So if you do P minus P dash, your P dash value matrix, what was there? The signs will get reversed. So if you have the solution, you can give me what is theta B, theta C, and theta D from that. Also, we came across some moment values which were not matching in the frame what we had taken. So I hope you have tried correcting that. Slope deflection equation or matrix multiplication. Okay, so we'll finish it over here. Try to find out these values of theta B, theta C by solving the matrix over here. Okay, so we can exit if you are given the attendance. And finally, you have to put them in slope deflection equation to get the moment values.